Okay, so let's talk now about a numerical technique to connect voltage or electric potential with charges, one called method of moments. So for that, I want you to consider the following problem. Let's say I have some weird shaped metallic object like this. Right? This object is a perfect conductor. A metal is often a good approximation of a perfect conductor. And let's say I've got a bunch of electric charge that's sitting on the surface. All right, one thing that we know about electric conductors, as we talked about in an earlier lecture, is that all electric charge in a conductor is going to build up at the very edge. It's not going to go inside. It's going to be all at the very edge. And the charge is going to build up in whatever way it needs to ensure that the electric field inside this object is zero. There's no electric field. Right, so if the electric field is zero inside this object, that also implies that the entire object is at the same potential. All right, and that makes sense because this is a perfect conductor, so it's got an infinite number of free carriers that can move around as they wish. If there is any change in potential from one place to another, then charges will immediately move in that direction. You're going to have a force, and the charges will keep going until it cancels out the electric field that you're trying to apply. So it's a little bit like if you've got a mountainous territory and you're defining the potential as altitude. If all of a sudden you make everything super slippery, that you have no grip and you can't walk around, then everyone is just going to fall down to the lowest altitude that they can. And that's kind of what goes on here, right? All of the electrons are going to sort of fall downwards to the lowest possible potential until the whole surface of everything is smoothed over. And so there's no changes in altitude or no changes in potential. All right, so the question we want to ask is, how does the voltage compare to the actual charge that are sitting on the outside? Where is there's lots of charge? Where is there not a lot of charge? What does it take to distribute that, right? Is there going to be lots of charge built up here? Or is the charge going to build up over here? Where's the charge going to build up? So that we're going to have a method called the method of moments that's going to give us that answer. Okay, the method of moments is a numerical technique that enables us to connect charges to voltage. And the way this is going to work is we're going to take our object and we're going to divide it up into a very large number of small squares that cover the entire object. And we're going to sum up the contributions of all of those squares together in order to figure out how the voltage and how the voltage and charge relate to each other. All right, so if we take our definition of what is the potential from the sum of all those charges, we're going to write the following. First, let me just define a couple terms. Rho Sj is the surface density of patch J, right? So there's going to be a lot of different patches, right? Let's say there's going to be n minus, we're going to say there's n patches in total. All right. So rho Sj is going to be the surface density specifically of the jth patch, right? And there are n of them, but that's just one of them. All right. Then we're going to have a delta Sj, which is the surface area, or really just the area of the jth patch. All right, let's keep going here. I'm going to find one or two more things. We're going to have a vector r prime j, which is a vector from the origin to patch J. Right, so before we set up a problem like this, we're going to have an origin. And we're going to have a vector that points from the origin to one of those little patches in the surface. All right. And one more. We're going to have the same for I, because we're going to have two different patches in a second, right? So r prime of I is the vector from origin to patch I. All right. So with this in mind, let's try to sum up the contributions of all of these charges together. And so for that, oops, let's take a look at this diagram right here. And let's say this patch right here, the one that I'm now coloring in green, we're going to call that the ith patch. And we're going to ask the question, how do all the other charges across this surface contribute to the voltage at the ith patch? And we're going to sum up all those contributions. So basically, we can treat it as if there is a little charge in every single one of these other surface boxes or surface grids. And then we're going to ask, what's the voltage at the ith patch from every single one of those? And we're going to sum those up. So that's going to look like this. And it's going to be V0 I, right? This is the voltage contribution of all of the other charges specifically on the ith patch, equals, we're going to sum up all those contributions, and we're summing up all the j patches from j equals 1 to n minus 1, because there's n minus 1 other patches that contribute. And then we're going to have a rho Sj times delta Sj divided by 4 pi epsilon times the absolute value of r I minus r j, right? This part down here, this absolute value, is sort of our replacement for r, right? It's a distance from the charge to the location where you're observing or calculating the potential. In this case, it's just a difference from the jth patch to the ith patch, right, where we're actually calculating things. So that would correspond to basically this line right here that I just drew in green and put that in black. Right, this line right here, that would correspond to Ri minus Rj. And we're just taking the length of that line. Oops. All right. And then rho Sj delta Sj, this basically is the total charge in the jth patch. Right? This is our replacement for Q of the jth patch. Right? And we're adding up the contributions of all of the other patches on patch I. And so that's going to be this contribution, and V0I is going to be the total voltage that we expect on the ith patch from all the others together. All right. Now here's the thing: we can take this equation and we can repeat this for every single patch that's on the surface. Right? We can sum up the contributions of all the other patches onto it, and in doing so, we're going to get a system of equations that has n different equations. And we also have n unknowns. The unknowns in this case are the rho Sj's, right? That's what we don't know. And we can basically invert that equation. We can figure out what the charge density is. And the way we're going to set that up is with the following matrix equation. We're going to have A times rho S equals V. V for voltage. All right, so let's talk about what each of these is. V is an n by 1 column matrix, or column vector, really. Each of which is V0 I, right? So this is going to be V0 for the first patch. This will be V0 for the second patch, onwards, and then V0 for the nth patch. And each of these voltage basically computed with this determination. So we don't know what rho Sj is. It's going to be in there as a variable, but you can figure out what that total sum is and just and keep it as a variable. All right, so that's what V is. The rho S is also a column vector that looks like this. It's rho S1 and rho S2 onwards to rho Sn. All right. And the A vector is going to be an n by n matrix that's going to relate the charge to the potential. All right, so this is going to be A11, A12, onwards to A1n, and this goes on to AN1, AN2, onwards to ANN. All right, so this is the matrix right here. And let me just tell you what each of the entries in this matrix is. A, I, J, the ith row and the jth column will be the following. Oops, that's not it. This will be delta Sj over 4 pi epsilon times the absolute value of Ri minus Rj if J does not equal to I. And the second part is basically going to be what you put in for the matrix when you're talking about a cell's contribution to itself, right? If I have a small little square and the charge is actually evenly distributed to it, how does the charge within it contribute to its own voltage? And for that, there's an approximation that's often used, which is the square root of delta Sj divided by 2 square root of pi times epsilon, and this is if J equals I. All right. So the idea is you've got this this weird amorphous shape, and you start out and you define some grid or some set of patches around it. Right. You know all the area of the patches, and you know the location of the patches because you've predefined all that. So from that, you can calculate what the Ri and Rjs are. You can calculate what the delta Sjs are because you know what the surface area of each patch is. And so all those are constants that you've pre-computed given the geometry that you set up. And the only thing that's not known here are the rows. The rows is what we're trying to calculate, and the V0s. All right. And so if you place all this into an equation, you can then very easily invert, since everything is known, and we can just say that rho S equals the inverse of A times V. And so this is a quick way to take something we don't know, rho S, and calculate it by computing this A matrix. And the A matrix is just populated with all the cells that follow this form. And the V are the actual voltages. Right now, in the case of the perfect sphere, or in the case of this patch with a perfect conductor on it, we also know that all the voltages are the same. This whole thing must be at the same electric potential, in which case V becomes very simple. V becomes something like 1, 1, 1, 1, 1, right? It's the voltage across the entire thing, and everything is the same. And so this becomes pretty straightforward. And so as V scales, you can figure out exactly what happens to the charge density in order to get that voltage. So this allows you to take any shape, any object that has a voltage distribution across it. And if it's a perfect conductor, then the voltage is going to be the same across this entire object, and quickly invert to answer the question, where are you going to get charge building up in order to give you that voltage distribution, right? So this, again, is called method of moments. This is a very, very useful technique. It's often used to calculate capacitances, for example, because capacitance, right, if you remember the parallel plate capacitor in circuits, and we're going to see this later, Q equals C times V, that the charge that's built up on this plate is equal to the capacitance C times the voltage difference between the plates. And so if we can have some relationship between charge and voltage, then we can figure out capacitances. And method of moments is a very useful technique to in fact do that. All right, it just requires dividing up your object or your surface or your geometry into these small patches. Because this is an approximation, however, it's important that the patches be small enough that your approximation is pretty good. If you take this blob right here and you've got very big patches, your approximation is not going to be good because you're treating the charge density within each of these patches as if they were constant. And for an object like this, it probably varies. So you basically want your patches to be small enough to capture the actual variations across your object. And the way you can know this practically is if you're calculating what the charge density is. If you take your patches, you make them a factor of 2 smaller, and you get the same answer, you know you're on the right track. The flip side, of course, is if your patches are way too small, then this computation starts to blow up and gets very complicated. This matrix A is n by n, and so if you double the number of patches, now you got to invert the matrix is larger and larger and larger, and that's computationally difficult. So that's the limit on the other side, is you want to have small enough patches that this approximation is accurate, but large enough that your computation doesn't blow up. It doesn't just take forever. All right, so that'll conclude this lecture on scalar potential and gradient.